Okay, so we know that these quasars, these dots, look like rather faint typical stars, but have much higher redshifts, so they're much further away. That presumably indicates that they must be vastly more powerful, brighter, have much greater luminosities than stars. But just how bright? That's what we're going to work out now, and the answer is pretty scary. So to make it concrete, I'm going to pick the quasar 2138 minus 4427 because I know it very well, and we're going to work out its luminosity. What do we know about this quasar? We know it's got a redshift of 3.23, and it's got a flux, that's the radiation from this quasar measured on Earth per square meter, of 1.3 by 10 to the minus 14 watts per meter squared. Now that's a very hard thing to measure actually, because this radiation comes at all different wavelengths. Some of it's X-rays, some of it's ultraviolet, some of it's infrared, some of it's visible light, some radio. And so it needs a whole bunch of telescopes observing at a whole bunch of wavelengths to add them all up. But anyway, that's what it comes out as. And what we want to now do is work out the luminosity. First step is to convert this into a distance. So we know space is expanding, so we've got A of t against time t. We know today A of t is 1. And let's assume, as a rough approximation, that A of t just goes linearly with time. We know, of course, that dark energy means it actually goes something like that. And for the real calculation, we'll have to take it into account. But let's just take it as going straightforwardly with time, and that'll give us a pretty good estimate. We know that this redshift 3.23 corresponds to a scale factor AT equals 1 over 1 plus Z, which comes out as about 0.23. So that means the light that we're seeing set out here at 0.23, and so this is the time the light has been travelling to reach us, multiplied by the speed of light, and you get a distance. Now we know from Brown's calculation the universe is about 14 billion years old, 14 gigayears. This is 0.23 times 14 gigayears, and 0.23 times 14 is about 3.3 gigayears. So this must be the rest. So it's 14 minus 3.3. So that means the distance is roughly 14 minus 3.3, which is 10.7 billion light years. Now I'm going to gloss over something here. What do we actually mean by distance is a rather tricky situation. Remember, space is expanding. This is how long the light has been travelling, but of course the space now would be bigger than that because space has expanded. When light started off, the universe was quite small, and as it's got here, space has got bigger and bigger, so the light has been travelling through a constantly expanding space. So in fact, we have distance is not a straightforward thing at all to calculate. For the purposes of this course, we're not going to worry about that too much, but bear in mind we do have to think a lot about what exactly we mean by distance, given it's changing as we go, and we'll come back to that in the cosmology course. But anyway, that's given us an estimate of the distance. Now let's work out the flux. Now you may remember the equation, the inverse square law. The flux from something is equal to its luminosity divided by 4 pi the distance squared. Now that's not quite right in cosmology. The trouble is, this is just assuming the light spreads out in all directions, so we had some source and the light goes in all directions, spread over a bigger and bigger sphere. But in cosmology, when space is expanding, there are two additional effects. First of all, each photon as it travels gets stretched into a longer photon, which means its energy goes down. So the energy of each photon is proportional to 1 over 1 plus the redshift, so to the scale factor. As the scale factor gets bigger, the energy goes down. In addition, let's imagine we have a whole bunch of photons flying along. Let's say there's, I don't know, 1 meter between each of them. As time goes on, the space between them will get stretched, so there might be 2 meters between them, or 3 meters. What that means is the number of photons you get per second goes down because the space between the photons has been stretched. There's a bigger interval. So that gives you the rate of arrival is also proportional to 1 over 1 plus the redshift. So, in cosmology, the true equation for things that are far enough away for the redshift to matter is actually this. 1 plus the redshift squared on the bottom is an additional term. And also, as I said earlier, we have to worry about exactly how we define d, which is not trivial at all, but for the moment we'll ignore that. So we've got this. We can rearrange it. So we get that the luminosity equals the flux times 4 pi d squared times 1 plus the redshift squared. And if you plug in the numbers, we know the flux, we know the redshift. That comes out at 3.4 by 10 to the 40 watts, which is a very, very big number. Of course, astronomy is full of big numbers. We can give it a bit of perspective by comparing it to the luminosity of the Sun. The luminosity of the Sun is 3.8 by 10 to the 26 watts. So this, the luminosity of this particular quasar, is about 10 to the 14 times the brightness of the Sun. So this dot, this tiny thing, is as bright as 10 to the 14 stars. Even the entire Milky Way galaxy only as bright as 10 to the 10 stars. This is 10 to the 4 times as bright, and 10,000 times brighter than a whole galaxy. This is a seriously bright object.